Viewers, this is U.A.C.E taking you through A-level physical chemistry. Now in this video, we are proceeding with physical equilibria, and in this video, we are going to be resuming or starting three-component systems. Now in the previous videos, we were only handling two-component and one-component system. So this video is presented to you by U.A.C.E and you are advised to subscribe to the channel and share it to your friends so that you can all benefit as a family. So we are resuming with three-component systems, and in three-component systems we are going to start with some definitions or some explanations that are going to briefly introduce us to the topic. So the major heading is going to be the three-component systems. Now, as an advice for those of you who don't have the notes, you are advised to pause the video on each and every slide. Say that you first take the notes and you resume the video for explanations. So you are saying that the three-component systems, and this is going to be our major heading. So you are saying distribution of a solid between two immiscible solvents in contact. So majorly we are going to be looking at two solvents that are being mixed, but these two solvents, they are going to be immiscible, or they must form a non-uniform solution. Say that when we mix them, they give us an immiscible mixture. Now after doing that, we get a solute which must be non-volatile, and we dissolve it in that mixture, and then we rapidly check that mixture so that that solute dissolves properly in each of the solvents. And at equilibrium, then we start determining whatever we are being prompted to determine. So that's a brief recap about the topic. That's what we are saying in this paragraph. If a solid, and we are saying that a solid can either be a solid or a liquid, is shaken with two immiscible solvents, like I've explained, in contact. Remember that these solvents must be in contact because you have mixed them. And everything being carried out must be at a given temperature. And we are saying that, so for the full paragraph, we are saying that if a solid can either be a solid or a liquid, is shaken with two immiscible solvents, and these solvents must be in contact at a given temperature. It is going to be soluble in both of those solvents, and we are saying that this solute is going to distribute or partition itself between the two immiscible solvents in contact until equilibrium is established. So when putting our solid into this immiscible mixture, we shake that mixture, it may be in a bottle, and we make sure that at equilibrium the solid is going to distribute itself in either of the solvents present in that mixture. So we are saying that at equilibrium, the ratio of concentration of a solid in one solvent to the other. Remember, when you use the word ratio, we must see this component to join sentences, and this one can also mean division in chemistry. So we are saying that at equilibrium, the ratio of concentration of the solute in one solvent to the concentration of the solute in the second solvent is always constant. So this one is very important. So we are saying that the ratio of the concentration after the solute distributing itself, the ratio of the concentration in one solvent to the concentration in the other solvent is always going to be constant, provided temperature is kept constant. Now this is what I've been emphasizing. If you look at physical equilibria, right here from where we started, I've always told you that there must be a condition on your definitions, or on whatever explanations you are giving. Now, what if you don't put conditions? Now you are going to find that if you miss out conditions on your explanations, your work is always going to be marked wrong, or you won't be awarded a mark for your definitions. And similar applies to your explanations. So the examiner will only write a word seen and he proceeds to the next number. So proceeding, we are saying that the partition or distribution law. Now I want you to notice that the partition and distribution law comes from this. So we are saying that now the partition and distribution law, whenever you are stating a law, every condition must be stated or must be within as a law suggests. You are not supposed to change anything. And you are saying that the partition and distribution law, it will state that a solid that is soluble into immiscible solvents in contact. Remember that those immiscible solvents must always be in contact. So this is a very key word. It is going to distribute itself between those two solvents that are in contact in the ratio of its concentration in one solvent to its concentration in the other solvent at equilibrium is constant at always a fixed temperature, provided the salt remains in the same molecular state in both solvents. Now if you look at this law, this is a very long law, and to memorize it, you need to sit down and you note down the key points. Now the key points in here, you will see that you have immiscible solvents that are in contact. So when you're summarizing, you should note that whenever you are writing this law, you shouldn't miss out immiscible liquids that are in contact. That condition must be there. And then you also talk about the distribution. Its distribution is going to be in such a way that the ratio, so you should also include this word, the ratio. The ratio of its concentration in one solvent. Say that the ratio of its concentration in one solvent to the ratio to the concentration in the other solvent at equilibrium. Now this is very important because this only occurs at equilibrium. At equilibrium is always constant, provided temperature is kept constant. And the solute must remain in the same molecular state in both of the solvents. Now that means that the solute should not undergo either dissociation or association. So you should know those keywords. So the keywords we have seen here, that must be in your law when you're stating it. We need to see immiscible solvents that are in contact. And after talking about immiscible solvents that are in contact, you talk about the distribution of the solute that we are going to dissolve in those immiscible solvents. And you say that the solute is going to distribute itself such that the ratio of its concentration in one solvent to the other solvent is always constant at equilibrium, provided temperature is kept constant. And the other condition, which is very important, is that the solute must remain in the same molecular state. And we have said that the solute remaining in the same molecular state in both of the solvents can also mean that the solute must not undergo association or dissociation. Now proceeding, we are saying that the constant ratio that we are talking about is also known as the partition or distribution coefficient. So it's always denoted by KD, and this we are going to use this very often. So let's proceed. Now after defining the partition or distribution law, now we are going to define the KD. Now remember that they have same conditions, but they vary in how they are stated, so do not confuse the two. I told you to always discuss physical equilibria with your classmates or with your fellow deskmate so that these conditions become a part of you and they must be at your fingertips because physical equilibria is one of the commonly said topics in your curriculum. So proceeding, we are going to be looking at the partition or distribution coefficient. Now in the previous slide, we have said that it's a constant. So how are we going to define it? That means that when you're setting a definition, I want to see a word called constant. Without this, you are defining something else. So that's why we are saying this is the constant ratio. It's going to be the constant ratio of the molar concentrations of a solid that has been dissolved in two immiscible solvents. But I've told you that whenever I talk about immiscible solvents, these solvents must always be in contact. So that's very important. The immiscible solvents we're talking about must always be in contact. Say that, and when equilibrium is established, when equilibrium has been established, so look at those words that are repeating. The words that are repeating are the words that you shouldn't miss in your definitions. And when equilibrium has been established at a fixed temperature, this is also repeating. At a fixed temperature, the molecular state of the solid must remain the same in both solvents. And they say that for molecular state remaining the same is the same as saying that the solid should not undergo dissociation or association. So briefly, or outlining it, you can easily define it as the constant ratio. The word constant is very important. Of the molar concentrations of a solid that has been dissolved into immiscible solvents. But when you talk about immiscible solvents, you must tell us they must be in contact. And then you talk about equilibrium. Say that at equilibrium, provided temperature is kept constant, our solid is going to remain in the same molecular state in either of the solvents. And we are saying that if a solid X is shaken between two immiscible liquids A and B that are in contact, provided temperature is kept constant and equilibrium has also been attained, we are going to say that our constant, which is also known as Kd, is going to be got by the molar concentration of X as dissolved in A divided by the molar concentration of X as dissolved in B. So in other words, Kd is equal to molar concentration in A is equal to the ratio of the molar concentration in A to that of the molar concentration in B. So this is what we are going to be looking at mainly in this video, and mainly all the calculations that we are going to be looking at are surrounded by that formula. Now note that whenever you are being given a question, the question determines the arrangement you are going to use. When they start with A, molar concentration in A, you should also put A on top. When they start with molar concentration in B, you should put B on top. When they start with molar concentration in A as the last one, you should put it at the last. So we shall be looking at that as our examples. Now proceeding, we are saying that the value of partition coefficient Kd is always independent of the volume of solvents used and the mass of the solid that is being used for any particular experiment at any given temperature. So we are given a question here, and this question here is prompting us to apply this formula. So we are saying that, so you write down the question, say that we follow up each other on the explanation part of the solution. So you're saying that 10 grams of butanoic acid is being added to 1,200 centimeters cubed of water and shaken with 150 centimeters cubed of ether. and this is kept done at a constant temperature, which is always our room temperature, and which is 25 degrees Celsius. And this is the temperature where we carry out most of the experiments involving partition or distribution coefficient. So always in physical equilibria, temperature is not important in our calculations, but when you're carrying out experiments, always temperature is important. So we are saying that at equilibrium, 3.6 grams of butanoic acid had remained as our part B. At equilibrium, 3.6 grams of butanoic acid had remained in the aqueous layer. Now part A, you are being prompted to calculate for the distribution coefficient of butanoic acid between Roman number 1, water and ether, and Roman number 2, ether and water. And part B, you comment on the solubility of butanoic acid in water. So we are going to be looking at all that. As a solution, for solution number 1, we are told that for part A Roman number 1, the mass of butanoic acid in ether is going to be 10 minus 3.6 because 1 for either was given at 3.6. So how do we get the one for the other? So we shall get the total mass and then you subtract the other component and then remain with 6.4. And we are saying that for KD, partition coefficient, like I told you, it will depend on the question asking. So the question was asking for find the partition coefficient between butanoic acid in ether and water. So they started with ether, that's why you placed molar concentration of ether upwards and you placed molar concentration of water downwards. Now as you are taking your notes, notice that these ones are square brackets. These ones are square brackets, and in chemistry, square brackets indicate molar concentration. So pay attention to that. So partition coefficient Kd is going to be equal to molar concentration of butanoic acid as concerned in ether to the molar concentration of butanoic acid as dissolved in water. So how can we get molar concentration of a substance? Always molar concentration can be in terms of grams per volume. That's why we get grams of this, which is 3.6, and we divide it by volume. That refers to a concentration. You can easily measure concentration in mass per volume. So that's why we say that 3.6 divided by 100 centimeters cubed of water in which it was being dissolved. Then divided by 6.4 divided by, now ether, the volume of ether was 100 and the volume of water was 150. So that's why we are having different volumes here. So you get a mass and then you divide it by its volume. You also get a mass divided by its volume. And lastly, we shall have our KD if you put everything in the calculator at once. Now, when you're answering paper 1, you are not advised to skip these steps because you are going to lose marks. Because each and every step is going to carry a marking point. So the more you skip steps, the more you limit your marking points. So KD, you write one step here to show simplification of both the numerator and simplification of the denominator, and then you put them in the calculator at once so that you can come up with the final answer as 0.844. So pay attention to that. And then Roman number 2, we are going to set that partition coefficient, which is also denoted by KD. And this D is always a subscript. So note that it's a subscript that is a capital letter of D, and K is always a capital letter. So whenever you're writing, make sure that you are very attentive on that because we mark handwriting in chemistry. So you're saying that partition coefficient is going to be given by the molar concentration of butanoic acid as dissolved in ether divided by the molar concentration of butanoic acid as dissolved in water. So as dissolved in ether, we are going to have 6.4. 6.4 divided by 150, and then 3.6, which is the remaining mass, divided by 100, and you end up with 1.185 partition coefficient as a constant. Remember, KD does not have units because it's a ratio. Now, I know some of you are not understanding this. For currently, we are going to dive into its details the further we go after you understanding some concepts. Here we just want to compare these values. It was the main purpose of this calculation. But you are going to dive more into the explanations of these calculations further in the video. And you are saying that part B, that we are going to say that butanoic acid is less soluble in water than it is in ether, because when you compare this one, this value, and this one, which one is higher? The one which is higher is going to be for this one. And we are saying that butanoic acid is less soluble in water than it is in ether, and the reason for that, we shall say that this is because it is 1.185 times more soluble in ether than water, like we have compared these results that you have got here. But you are going to look more for these explanations as we go on with the video. Now looking at some of the limitations of partition coefficient. Now remember, limitations for partition coefficient are the same as conditions. And I want you to note that for physical equilibria, always we pick the conditions from the definitions. So you have to pay close attention to that. Now for physical equilibria, always temperature should be kept constant. So you always never forget this point because it's a rescuing point, it's a rescuing answer. Even if you don't have the answer and they ask you any condition about physical chemistry, most of the experiments of physical chemistry, we carry them out at a constant temperature. So at least you write temperature must be kept constant as one of your answers. And then the solute, our solute, the solute should be soluble. As one of the conditions, the solute should be soluble in both of the solvents. Now, on mixing these miscible solvents, we get a non-uniform solution, and then we add a solute, which can either be in terms of a solid or a liquid. And we check this mixture vigorously so that our solute can dissolve or can be soluble in both of the solvents. So the solute must completely dissolve or it must be soluble in both of the solvents. Like a solid being dissolved should not isolate itself from the solution. And we are saying that the solute must not dissociate or associate in either of the solvents. Now I've already explained this. Dissociation, you have looked at this in colligative property. Dissociation and association, and I know what the effect, you should know the effect of it. If you haven't covered the topic of colligative property, it will also be uploaded on this channel for further explanations. So the solute must not dissociate or associate in either of the solvents. And we are saying that another word to group all these words can mean, you can represent it as the solute remain in the same molecular state. So our solute remaining in the same molecular state is the same as another student saying the solute must not dissociate or associate in either of the solvents. And we are saying that the solute must not react. Now we say that this solute must only dissolve The solid must only dissolve in either of the miscible solvents, but it must not chemically react with any of the solvents. So we expect the solute to just dissolve. It should just dissolve in the solvents but not reacting. Remember, dissolving is not reacting. So our solute must not dissolve or react with either of the solvent present in that mixture. And then lastly, our solid should not circulate. The solid that is being used, it shouldn't circulate either solvents. Like when you dissolve into the solid into the immiscible mixture, it shouldn't be just one-sided in one solvent. The solid should distribute equally in either of the solvents without concentrating only in one solvent. So that's why we are saying that the solute should not circulate either solvents. Now we are going to look at experiments. Experiments on how to determine partition or distribution coefficient. Now experiments for physical chemistry are one of the easiest because after reading the experiment, you should imagine it in your head. As you are reading experiments, try to imagine yourself practically doing it so that you can easily remember each and every line of the experiment. So in this experiment, we are going to be determining the distribution coefficient of a solute that has been dissolved into two immiscible solvents, but these immiscible solvents must always be in contact. And for Roman number 1, we are saying that a known mass of a solute. Now as we are starting, I've told you, for you to quickly remember experiments, you make sure that you are imagining what you are doing. You can even pick a cup and you use your home utensils to quickly remember these experiments. You can do it practically using your home utensils so that you can do it physically and your mind can easily remember it once you are being asked for it in the paper. Because we usually ask these experiments and they are given over 7 marks. So starting, we are saying that a known mass of a solid is being dissolved. Is dissolved in known volumes of two immiscible solvents, but these immiscible solvents are always in contact, and this experiment is carried out in a separating funnel. And we're saying as a Roman number 2, the mixture is going to be shaken. The mixture is shaken so that our solid can completely dissolve in either of the solvents and then allow to stand for equilibrium to be established. Now the layers, now on standing allows two functions. It allows establishment of equilibrium. It also allows, remember these are immiscible mixtures that have been put in a separating funnel. It also allows these layers to settle, so that the solid, after distributing itself at equilibrium, the layers are settled and they are separate. That's why we are coming up with Roman number 3. The layers are then separated and the concentration of the solid in each layer is determined by titration. Now let me hope you cover this in O level and we repeat it also in A level. You'd use known volumes of these immiscible solvents and used a certain mass of a solid, a known mass of a solid. So you can easily determine the concentration of the solid in either of the solvents by titration. And you shall be looking at this using real life examples. So you're saying that the standard solution selected is going to depend on the following: on the nature of the solid. For example, if the solid is acidic, you're going to be using a standard solution of an alkaline. And such an alkaline solution, a good example of such a standard solution can be sodium hydroxide. And we're saying that it can be used as our standard solution. So Roman number 3, we are saying that if a solid that you are going to dissolve is alkaline in nature, then we use a standard solution which is acidic, and a good acidic solution that we have in the laboratory that is always standard, we always use hydrochloric acid as our standard solution. And we are saying that if the solid that is being used is iodine, remember that iodine, we don't know whether it's acidic or alkaline. So whenever we are using iodine, the standard solution we are always going to use is going to be sodium thiosulfate as our standard solution. Now how are we going to determine the endpoint? Always the endpoint, if you are carrying it out practically, is going to be detected by indicators that are selected depending on the nature of the titrant being used. So if you're using sodium hydroxide, there is a certain indicator for it. If you're using hydrochloric acid, there is a certain indicator for it. And if you're using sodium thiosulfate, there is a certain indicator you use. Now let's look at some of the major and commonly said experiments about this topic. So part A, we are going to be looking at determination of the partition coefficient of butanoic acid. And butanoic acid can also be known as succinic acid. That is going to be between water and ether. Now this is the procedure, or this is how you are supposed to present your flow. Now remember, I've told you, for experiments, you can easily even try to imagine it. If imagining is too hard, you can pick your home utensils and you try to do it practically so that you can easily remember when you are being asked such questions. That's why we are having our first procedure as a known mass of butanoic acid. Always remember that for the solid you are going to use, you are going to be using a known mass of butanoic acid is being added. Now this is going to be added to a known volume of water in a separating funnel. Always notice that our experiments are going to be carried out in a separating funnel. And on top of that, you are going to add a known volume of ether. Now after adding these two, we have formed our immiscible mixture, and we have made sure that these immiscible solvents, they are both in contact, and we have dissolved our non-volatile solute, which is always butanoic acid according to the experiment requirements. And we are saying that this mixture is going to be shaken. Why are we shaking? We always shake so that we can allow dissolution of this solute in either of the solvents, and we leave it to stand for equilibrium to be established. And this experiment must stand at a constant temperature. That's why we are saying the mixture is shaken and is sealed and allowed to settle. This settling is to enable this experiment or our apparatus to attain or establish equilibrium, provided our temperature is kept constant. And we are saying that the layers after equilibrium has settled, remember that we have given it time because we allowed it to stand. So we expect that in that separating funnel, the solid has distributed itself and has dissolved in either of the solvents. Now after doing so, what next? The layers are going to be separated because in our separating funnel now the liquid layers are clear and are clearly properly. So you are going to open the tap of the separating funnel and then the layers are going to be separated. And after separating them, we need to get concentration of the solid that has been dissolved in either of the solvents. That's why we are saying that. And the fixed volume of the aqueous layer is pipetted and is titrated against. Now this is an acid. That means that it's going to be titrated against a standard alkaline solution. And the fixed volume of the aqueous layer is pipetted and is going to be titrated against a standard solution of sodium hydroxide. Why are we using a standard solution of sodium hydroxide? Because the solid is acidic in nature. Butanoic acid will be titrated with a standard alkaline solution. And a good one for that, we said it will be sodium hydroxide. And then for sodium hydroxide, we usually use phenolphthalein indicator. Now after saying that word, after talking about pipettion and titration, you have to give an equation for the experiment. That's why we are saying that butanoic acid reacting with 2 moles of sodium hydroxide will give us a solid. And after giving us a solid, it will also form water. Now we are saying that from the volume of the non-standard sodium hydroxide that we use for titration, the concentration of our solute, which is butanoic acid, is going to be determined. But remember, is going to be determined in the aqueous layer, because that's where we picked a known volume, or that's where we pipetted our known volume of the solution. And then since butanoic acid is acidic in nature, we titrate it using a standard alkaline solution. And in this case, a good one in the laboratory is sodium hydroxide. So you have to pay attention to that. And we are saying that the aqueous layer is determined. So in proceeding, we are saying that the concentration of the acid, remember that you have got the concentration of the acid in the aqueous layer. Now what about the concentration of the acid in the organic layer? How is it going to be determined? So this is the purpose of the second statement. We are saying that the concentration of the acid in the organic layer is then obtained by subtraction. This is enough for it. Or a student can also give a full statement about pipetting again a non-concentration of a part of the organic layer and titrating it with a known volume of standard sodium hydroxide and finding the concentration of the solid 2 in the organic layer. So there are two conclusions. You either go with this one or you go with the other longer one. But I found this one to be more efficient and time saving, because in paper 2 you have to be writing a lot of things. So the concentration of the acid in the organic layer is going to be determined by subtraction. And then partition coefficient, just how we defined it, the partition coefficient is going to be obtained from this expression. And we are saying that Kd, which simplifies for partition coefficient, is going to be equal to the molar concentration of butanoic acid as dissolved in water is the ratio of the molar concentration of butanoic acid as dissolved in water to the molar concentration of butanoic acid as dissolved in ether. And I told you, remember that these are square brackets. So as you are taking your notes, make sure that you write square brackets. And also the note for Kd, D is a subscript. D is a subscript. This is not on the same level as K. So you always put it as a subscript. And then K is capital. Now in proceeding, we are going to be looking at another experiment. But this time round, you are going to be titrating iodine, which is neither acidic nor alkaline. So for iodine, we say that the standard titrant is always going to be sodium thiosulfate solution. and it's always the standard titrant that determines the indicator you are going to use. Now note that the experiment flow is going to remain the same. What's only going to vary are the reagents that we are using. So this is what makes the experiments of partition coefficient or distribution coefficient very easy. So we are saying that when you're determining the partition coefficient of iodine between water and tetrachloromethane, you are supposed to follow these steps. And Roman number 1, we have said that a known mass of that solid that we are trying to find, a known mass of iodine, is going to be added to a known volume of tetrachloromethane, but this must be in a separating funnel to make a solution. So note that this is the same way we started our previous experiments, and this is how we are going to be describing each and every experiment still. And you're saying that a known volume of water is also added to this mixture and the funnel is stoppered. The word stoppered also means closed. We put a cork on the funnel. Why do we close our funnel? Because we are going to check this mixture, and we can't check the mixture if the funnel is open. So this word is very important. Stoppered means closing. So after mixing, after adding a known volume of water, you stop our channel. We stop our funnel. Sorry. That means that you don't have to say that when you are doing time to check, your solution doesn't get out of the flask. And you're saying that the mixture is then shaken. The mixture is shaken and then allowed to settle. Why are we allowing it to settle? For two things. One is to attain equilibrium, and this equilibrium is obtained always at a constant temperature. And the other is to enable, since we have immiscible mixtures, is to enable the two layers to separate fully so that they can form one distinct layer. But the main reason for allowing the mixture to settle is for equilibrium to be attained. And that equilibrium to be attained, it must be attained at a constant temperature. If you don't want to use the word attained, you can use the word I used here, established. And then Roman number 4, we are saying that the layers, after settling, the layers are then going to be separated. After the layers being separated, we always first pick an aqueous, I fix a given volume of the aqueous layer, and we titrate it with a standard solution. Now here we use iodine. That means that you are going to pipette a fixed volume of the aqueous layer, and we are going to titrate it with a standard solution of sodium thiosulfate, because I told you iodine is neither acidic nor alkaline. So the only standard titrant we have for it is the sodium thiosulfate. But we need to say this word because any titrant used in partition coefficient must be standard. And the indicator that accompanies that is always the starch indicator. And after talking about this statement of pipettion and titration with a standard solution, you should write the equation straight away. So we are saying that 2 moles of sodium thiosulfate are going to react with 1 mole of iodine in its aqueous state to form a salt or to form a complex and 2 iodide ions. So we are saying that from the volume, just like we said in the previous slide, from the volume of the standard sodium thiosulfate that was being used, we determine the concentration of iodine in the aqueous layer. Because use the known mass of iodine and use known volumes of the solvents, and the titrant you're using is also standard. So I believe that you can determine the concentration of iodine in the aqueous layer, and this is going to be determined by titration. So you can write that as your remarking point here. Is determined by titration. And we are saying that the concentration, furthermore, the concentration of iodine, our concentration of iodine in the organic layer is going to be determined by subtraction. Now I told you that also someone else can go the other way. You can also pipette a fixed volume of the organic layer and you titrate it with a known volume of the standard sodium thiosulfate. You also determine the concentration of iodine in the organic layer. That's an alternative option for these statements, but they all mean the same. So you go with the one which you find easier for you. So we say that the partition coefficient Kd, and I say that this K is capital, D is a subscript, and it is also a capital. So the partition coefficient Kd is obtained from this expression. So Kd is going to be equal to the molar concentration of iodine as being dissolved in water to the molar concentration of iodine as being dissolved in carbon tetrachloride. Now keep mentioning this, that these are always square brackets. Don't write curved brackets, because squared brackets are the brackets that show that you are dealing with molar concentration. And these words here, this word water, is a subscript of those brackets. Also carbon tetrachloride was supposed to be a subscript. So you give attention to that as you are taking your notes. So in proceeding, we are saying that part C, we are going to look at an experiment for determining the partition coefficient of ammonia. Now ammonia here is our solid. Now ammonia is an alkaline compound, so we are going to titrate it with a standard acidic compound. And whenever it's titrated with a standard acidic compound, we use methyl orange as our indicator, but here I made a mistake for phenolphthalein. So let's proceed. We are saying that determination of partition coefficient of ammonia between water and chloroform. And we are saying that, now remember that we are going to repeat the same procedures. So I'm just going to go through because I've already explained everything about stating experiments. So an aqueous solution of ammonia. Now here we are not going to use a known mass because ammonia doesn't exist as a solid, but you are going to get an aqueous solution. But this aqueous solution is going to be of known concentration and a known volume. That's why I say that of known concentration and of known volume is going to be transferred into our separating funnel. And then remember that an aqueous solution of ammonia is containing both ammonia as a solute and water. So pay attention to that. And then we are going to add the organic layer. Our organic layer is going to be trichloromethane, or also known as chloroform. It's going to be added to the solution in the separating funnel. Now after adding them, you have to stop at this funnel before you begin shaking. And then you say that the separating funnel is going to be stopped. Then I missed it here. It's added, the solution is added in the separating funnel and the funnel is stopped or it's closed. And they are saying that the mixture is then shaken and then left sealed to stand. We always leave it to stand at a constant temperature such that equilibrium is being established. Also the layers are given ample time for resting. And we are saying that the layers are going to be separated and a fixed volume of the organic layer is pipetted and is titrated against a standard solution of HCl using methyl orange indicator. After talking about pipettion and titration, you always write the equation. So ammonia in aqueous reacting with HCl is always going to form ammonium chloride. And we are saying that from the known volume, from the volume of standard HCl that's being used, we determine the concentration of our ammonia in the organic layer. And the concentration of ammonia in the other layer is always obtained by subtraction. And we are saying that partition coefficient is going then to be obtained from this expression. Always Kd, capital K and a subscript of capital D is going to be equal to the molar concentration of ammonia as dissolved in water, divided by to the molar concentration of ammonia as dissolved in carbon chloroform. So make sure that this carbon trichloride is a subscript of the molar concentration bracket, and also water must be a subscript of the molar concentration bracket as you are taking your notes. Now we are going to look at numerous examples to master what we have covered. And as opposed to Roman number 1, we are saying that in an experiment to determine the partition coefficient of ammonia between water and trichloromethane, 10 centimeters cubed of the aqueous layer require 13.2 centimeters cubed of 0.25 molar HCl. Now I want you to realize that whenever we are going to do our calculations, we are going to start with this statement from here, from 13.2 to 0.25 molar of HCl. That's what we start by interpreting. 1000 is going to contain this. Then what about this volume that they are giving us? Hope you are getting me. After interpreting that, you go to the volume that has started the question. So that's how we are going to be playing around with the logic. So pay attention to how I'll be calculating my work. And here, we are going to do the same here. 1000 will contain this. What about this? This is the second. After getting this, you go and get the volume that has started the question. So that's how our things are going to be framed. So 25 centimeters cubed of trichloromethane layer required 6.6 centimeters cubed of a 0.05 molar HCl for complete reaction. Now they are prompting us or requiring us to calculate the value of the partition coefficient. Now here we are going to say that solution. How is that question going to be attacked? First of all, you are going to start with this aqueous layer. Now let me highlight this a bit. I said that we start with this statement. You first interpret this. This one here, 0.25 HCl molar. 0.25 HCl molar means that 1000 centimeters cubed of a solution contains 0.25 moles of HCl. That's why we start in our solution. You're starting with molar concentration of ammonia in the aqueous layer. So we need to first find the number of moles of HCl that reacted with ammonia. And we shall start with this standard solution. So 1000 contain 0.25. Then what about the volume that we used? We used this volume. 13.2 contain what? That's why you're seeing this. 13.2 is going to contain 13.2 times 0.25 divided by 1000 moles. So the moles it's going to contain is going to be 3.3 exponential negative 3 moles. So let me hope you have seen that. And that's how we are going to, after doing that, you write the equation straight away. So let's first look at that. Writing the equation, since we have got number of moles of HCl that reacted, after getting number of moles that reacted, always know that you are supposed to write an equation immediately. So ammonia reacts with HCl in the ratio of 1 to 1. So 1 mole of ammonia in its aqueous solution reacts with 1 mole of HCl to form 1 mole of ammonium chloride. So how can we get the number of moles of ammonia in the aqueous layer? That means that since mole ratio is 1 to 1, the moles of ammonia that reacted are going to be the same number of moles of HCl that reacted. So that means that 3.3 moles of ammonia are present, or they are the moles that reacted. Now, how can we get the molar concentration of ammonia? Because these are moles. So we need to know these moles were contained in which volume, and this is always the volume that started our question, or that started the statement, or that started the paragraph of the question we are dealing with. So you go from your right hand side to your left hand side when you're interpreting such questions. That's why we said that these moles here were contained in that volume that started the question. So that means that we are saying that 10 centimeters cubed 10 centimeters cubed of the aqueous layer contain 3.3 exponential negative 3 moles of ammonia. Then what? Because we want molar concentration, we want to know the number of moles in 1,000 centimeters cubed. That's why we say that. What about 1,000? 1,000 centimeters cubed of the aqueous layer is going to contain 1,000 times 3.3 exponential negative 4 divided by 10. And if you use your calculator, you are going to end up with 0.33 moles per dimeters cubed, or molar. Now this is the molar concentration of ammonia in the aqueous layer. Now let's do the same to find the molar concentration of ammonia in the organic layer. Like I told you, in the organic layer, we are going to start by interpreting the concentration which was given. So if interpreting the concentration which was given, moles of 1,000 moles of the acid required contain 0.05. Then what about 6.6? And 6.6 contain these moles, which is 3.3 exponential negative 4. Now we have done the equation already, so you just compare this, the mole ratio. Since mole ratio is 1 to 1, number of moles of ammonia that reacted are going to be equal to the number of moles of HCl that reacted. And this is the same, 3.310 per negative 4. Now these moles are going to be contained in that volume. That always starts that question. I'm not telling you to cram, you should be good at analyzing those questions. I'm just giving you a simpler way to analyze them, however weak you are. So the volume that started the question was 25, so 25 centimeters cubed, or that started that paragraph, or that sentence we are on. If you look at that question properly, whenever you're calculating these numbers, you look at that question and read it by yourself so that you can know how to interpret it when you are in an exam. So 25 centimeters cubed of the organic layer contain these moles. Then, because we need molar concentration, that's why we shall determine what about those ones in 1,000. So that's why we say, what about 1,000? So 1,000 centimeters cubed of the organic layer is going to contain 1,000 multiplied by those moles divided by 25. And then you also get the molar concentration of ammonia in organic layer. Now, how is partition coefficient got? So partition coefficient is got by molar concentration of ammonia. These ones are square brackets. These are square brackets. Molar concentration of ammonia as dissolved in water divided by molar concentration of ammonia as dissolved in the organic layer. And we say that the arrangement depends on the question. The question requested you for partition coefficient of ammonia dissolved in water to that dissolved in organic. So you have to arrange them that way. If the question was organic to water, you arrange your ratio in terms of that way, because we need you to be part of us when you are making the marking guides. So molar concentration of ammonia as dissolved in water was found to be 0.33, and molar concentration of ammonia as dissolved in the organic layer was found to be 0.0132. Now once you divide all that, you'll find that on your calculator you'll be getting 25 as your KD. Now I say that KD does not have units. Reason being, number one, it's a ratio. Okay, the number two now you can do it on your own according to what I've explained, but I'm going to do for example so that you can know it's possible, and I explain everything so that you can do the other numbers on your own. So interpreting the question, they have told us that 50 centimeters cubed of 1.5 molar ammonia solution was shaken with 50 centimeters cubed of trichloromethane in a separating funnel. And after that, they say that after the layers had settled, remember that this is attaining equilibrium, 20 centimeters cubed of trichloromethane layer was pipetted and titrated with 0.05 molar of HCl. Now they are saying that 22.9 centimeters cubed of the acid was required for complete neutralization. So you are being prompted in Roman number 1 to write the expression. That can express partition coefficient between ammonia and that of water, and for ammonia between water and the organic layer, and this time round the organic layer we used was trichloromethane. Roman number 2, you are being prompted to calculate the value of the partition coefficient. So for Roman number 1, the expression for partition coefficient, now they asked expression for partition coefficient. The question was in terms of arrangement between water and trichloromethane. That means that in the numerator, you must have molar concentration of ammonia in water to the molar concentration of ammonia in trichloromethane, because that's the question arrangement, and that's what I've been talking about in terms of arrangement of this. So let's proceed. We are saying that the expression is going to be given by KD. KD is going to be attained by molar concentration of ammonia as dissolved in water to the molar concentration of ammonia as dissolved in carbon trichloride. I've been telling you that, and I'll keep telling you that this is square brackets. Square brackets indicate molar concentration in chemistry. But if you use curved brackets, you'll be marked wrong because they don't indicate molar concentration. So Roman number 2 is now asking us to calculate for the value of the partition coefficient. Now such questions, they appear to be long, but you need to find the molar concentration of the solid in either of the layers, in the organic layer and in the aqueous layer. Now remember that for ammonia solution, it always exists as an aqueous solution, so we don't have the aqueous layer. Actually, the aqueous layer is ammonia itself as a solid being dissolved in water. So that's why we start with getting ammonia in the organic layer. Now the organic layer here we used was trichloromethane. So that's why I'm saying that we are going to first start by getting molar concentration of ammonia in the organic layer. Now if you look at the organic layer, they talked about organic layer, and what they gave about organic layer, they say that 20 centimeters cubed of trichloromethane layer was pipetted and titrated with 0.05 molar HCl. So we already start with the standard acid. So 1000 is going to contain 0.05 moles of the acid. Now what about the volume which was really required? In total we used 20, but what was the volume really required? And in total it was 50. But what was the volume which was really required? The really required volume is the volume that reacted, which was 22.9. So if 1000 centimeters cubed of a solution contains 0.05 moles of the acid, then what about the volume which reacted, which is 22.9, contain what? That's why we have in this expression. And we are saying that moles of the acid is equal to 22.9 times 0.05 divided by 1000, and you get 1.15 exponential negative 3 moles. Now, whenever I get moles that actually reacted, I've told you the next step is always forming an equation. And the equation for that is always going to be in terms of, if it's ammonia, it's always more ratios, most cases is 1 to 1 because you're reacting ammonia with HCl and you form a solid which is ammonium chloride. So ammonia reacts with HCl in a mole ratio of 1 to 1. That's why we are saying that number of moles of ammonia is equal to the number of moles of HCl. And these ones, that means that the moles we calculated here must be the same moles like the ones present down here, which is 1.145 exponential negative 3 moles. Now our next step, we want to get molar concentration, but remember that these are just moles. So these ones are contained in which volume? Because this is when you get that volume, we shall multiply by 1000 to get molar concentration that we are looking for. So if you are to look at the volume that we used 20 centimeters cubed. That means that 20 centimeters cubed of the organic layer contains that volume. So what about 1000? Because we need to get molar concentration. So 20 centimeters cubed contain the moles that we have calculated for ammonia. Then what about 1000 centimeters cubed of the organic layer? Is going to contain how many moles? So you do the math, you divide by 20 and then you multiply by this 100. And then you get 0.05725 molar as your concentration. Now to get the initial molar concentration of ammonia in the aqueous layer, we always get molar concentration of ammonia in the aqueous layer minus the molar concentration of the ammonia in the remaining. Okay, the total concentration was 1.5 is what we started with in the question. So this is the concept that we have been using in our experiments, that to get the concentration that has been remaining, we get it by subtraction, and this was a good example for it. So we get the initial concentration, which was 1.15, and then we subtract the concentration of ammonia we have got in the organic layer, so that we can get our molar concentration of ammonia in the aqueous layer. So to get molar, this is molar concentration of ammonia in organic layer. To get molar concentration of ammonia in aqueous layer, you get the initial concentration of ammonia that we used, and then you list the ammonia that has been dissolved in the organic layer, so that we can get the ammonia that has been dissolved in the aqueous layer. And partition coefficient, we have already quoted the expression, so here you just come and you substitute, or you can rewrite the expression once again, and then you express your answer to 2 or 3 decimal places, which in this case I got 25.2. And so we are going to the next question. So we are going to be looking at Roman number 3. But remember that we are going to use the same idea of answering. And we are saying that iodine in aqueous potassium iodide was shaken vigorously with an equal volume of tetrachloromethane. And Roman number 1, we have told you to state the role of potassium iodide solution. Roman number 2, we have told you to state and explain the observation made in A. Now part B, we have said that a certain amount of iodine was shaken with this and this. So you have been prompted to calculate this. So you are going to be handling each of them. Like I said, write down the question and look at how we are interpreting the questions. We always start with 1000 contain this, and then we go to this one. What about this one? And then the moles we get are always contained in this one. Then what about 1000? That's how everything is calculated. Also here, we are going to say that 1000 contain this. What about these ones contain how many moles? Now the moles contain this are the moles that are going to also to be contained in this one. Then what about 1000 is going to contain what? So always pay attention. So let's proceed to the answering. Now for part A, we are saying that potassium iodide. Potassium iodide is going to provide the iodide ions. The iodide ions in turn combine with iodine molecules, and in so doing they are going to form a soluble complex, and that soluble complex is going to be triiodide ions. Now we have already looked at this solution in group 7, which was a video which was also uploaded on this channel. So this is part of inorganic chemistry. And we are saying that iodine molecules that you have dissolved are going to react with the iodide molecules from potassium iodide. And you are going to form a soluble complex of iodide ion, triiodide ions. And we are saying otherwise may mean for any other solvent, iodine is going to just be sparingly soluble. That's why we are saying that otherwise, iodine is sparingly soluble in water. Now, from number 3, we are saying that the colorless organic layer, which in this case we use tetrachloromethane, is going to become purple. Now, you should carry out this experiment practically with your respective teachers because it's a very commonly said question. And the reason behind that is because iodine, which was present in our aqueous layer as a brown component, remember iodine is a brown solid, is going to dissolve in our organic layer. And in so doing, as it is dissolving in our organic layer, we are going to see our colorless organic layer turning to purple. That's why we are saying that aqueous layer finally becomes faint brown or pale brown, because now the aqueous layer is becoming faint brown because the iodine that was present in it is all going to the organic layer. So we are forming a purple color in the organic layer. So the organic layer comes from colorless to purple, whereas our aqueous layer, which had iodine being dissolved, and remember iodine is a brown solid, is going to fade, or is going to become faint brown because the brown is going away. The iodine is combining with the organic layer. The organic layer turning from colorless to purple, whereas the aqueous layer turning from brown to faint brown due to the dissolution of iodine in the organic layer. Now let's look at part B. What did part B require? So for part B, we are saying that we are going to start with finding molar concentration of iodine in the aqueous layer. And we have said that we have explained that we are going to get all these things. 1000 contains 0.05, like in the statement that you have seen. When you're writing the other question on the previous slide, I explained that. What about 6.7? So you get those moles. Those moles are in that volume that started the statement. So after getting the number of moles that reacted, I say that the next step is writing the equation. So for crammers, if you feel like you want to cram, you make sure that your third step or your fourth step is an equation, because this one also carries 1.5 a mark. So 2 moles of sodium thiosulfate react with 1 mole of iodine to form a complex and 2 iodide ions. So 2 moles, that's why we interpret it as 2 moles of sodium thiosulfate reacted to form 1 mole of iodine, reacted with 1 mole of iodine. Then what about these moles that we have calculated? Because the sodium thiosulfate that was standard, you always start with standard components, like you have been studying in your practical chemistry. So since 2 moles of sodium thiosulfate reacted with 1 mole of iodine, what about these moles? They are going to react with how many moles? So it will be 1, this one here, divided by 2 times these moles. and then you'll get 1.8425 exponential negative 4 moles. So that was your answer. So proceeding, if you are to proceed, we are saying that 25 centimeters tube to contain those moles. Then what about 1000? Because we want molar concentration. Remember that this 25 is the one that started that statement of yours, like I told you when you are writing the question. So 25 contain those moles you have calculated. Then what about 1000 centimeters cubed of the aqueous layer? It's going to contain which concentration? So it's going to contain these moles. So in the next line, we convert the moles to concentration. So the concentration that is going to be present in the aqueous layer is going to be 0.00737 molar. Now after getting molar concentration in the aqueous layer, we are also prompted to calculate molar concentration of iodine that was dissolved in the organic layer. So how are we going to do that? So molar concentration of iodine dissolved in the organic layer. First of all, it was sodium thiosulfate that was standard. So you do the same thing. 1000 contained this. What about 27.2? Just like I showed you how we interpret this. So you get 3.128 exponential negative 2 moles. And then from the reaction equation, like we wrote before, after getting moles reacted, you refer back to your equation. Always, you shouldn't forget that. So from the reaction equation, we are seeing that 2 moles of sodium thiosulfate reacted with 1 mole of iodine. Then what about the moles you calculated? Reacted with what? So it's going to be 1 divided by 2 times these moles. And when you do so, 1 divided by 2 times these moles, which is 3.128 exponential negative 2, you are going to get 1.56 for exponential negative 2 moles. So these are the number of moles of iodine that reacted with sodium thiosulfate. Now these moles are in which volume? Then the volume that started that sentence you are on, which is 25 centimeters cubed of the organic layer. So you're saying that 25 centimeters cubed of the organic layer contain those moles. What about 1000? We are multiplying by 1000 because we want molar concentration. 25 is not a molar concentration. So if 25 centimeters cubed contain these moles, then what about 1000? It's going to contain how many moles? So by getting this, you have got molar concentration of iodine in the organic layer, and we also got molar concentration of iodine in the aqueous layer. So we have these two. After getting those two, we are free to calculate for our partition coefficient. Now partition coefficient Kd is equal to the molar concentration of iodine as dissolved in the organic layer, and I've told you the arrangement depends on the question. So the question was in organic layer to water, so that's the arrangement we used. So Kd is equal to molar concentration of iodine as dissolved in the organic layer to the molar concentration of iodine as dissolved in water, and we have got the molar concentrations. So in the organic layer it was 0.6256. In the aqueous layer, it was 0.0073. So if you pick your calculator and you divide the two, you are going to get 84.88. However, I used 2 decimal places, but you are advised to always use 3 and above. So that was our partition coefficient. Let me hope the calculations are simple because there is the same concept that we use for calculation. We are going to pause the video. I've given you the solution for number 4, but you pause the video You write down the question and you try to interpret it on your own as an exercise for you to adopt the interpretation. Now, for the case of this video, I didn't include exercise work. So you're going to use this activity for you to learn how to interpret the question. And you find where the logic was such that you can be good at this question analysis. So pause the video and you take the question and you also write down the solution. First start by writing down it by your own, and then later try to come and see the solution and you follow what I did. So as we are proceeding, we have looked at applications of distribution or portion law or partition law. So correct this word here. It must be partition, not portion. So most of the applications we are going to cover them one by one, especially the most common one is solvent extraction. Now solvent extraction is the video that follows. Now the video that follows, we are going to entangle and we talk about each of these ones. So make sure that you subscribe and you be attentive for the next uploading video. So you're saying that some of the applications of partition or distribution law, we have solvent extraction. We also have investigation of complex ions. We have distinguishing bromides from iodides. We have ion exchange, and we also have partition chromatography. So you must know at least 3 or 4 of these ones, because for any question of partition coefficient that we said, we shall always ask you to label to give us at least 3 of them, or a minimum of 2. That's it for this video. This video has been compiled and presented to you by Yusuf. So for any inquiries of any statements of anything concerning biology, chemistry and math, you can reach me out on the following contacts. For those of you having exams who are soon sitting on their papers, success in your exams. For those of you who are continuing, I advise you to keep pushing. Everything is possible. So see you in the next video.